Hello learners, welcome back to the course on deformation processing of materials. In the previous class, we had seen the characteristic elastic and plastic curves for the rolling operation, and after that we started the next process, which was extrusion. In that we saw what is meant by extrusion, and we saw the typical division or types of extrusion, which are direct extrusion and indirect extrusion. So in today's class, let us now see some important characteristics and parameters related to the extrusion process. Okay, so let us begin today's discussion. Okay, so for the extrusion, basically the die should be made of die steel or any other material which is not easily worn out. Okay, so the die should be made of die steel and should be properly treated so that it does not wear out easily. Okay, and should be properly treated so that it does not wear out. Okay, so this type of property is required for the dies. Now let us see some mathematical parameters or control parameters which influence the extrusion process. So one of the terms is the extrusion ratio or the reduction ratio. Okay. So let us see what is meant by extrusion ratio. Or the reduction ratio. Okay. So this is nothing but the ratio of initial cross-sectional area to the final cross-sectional area. And it is denoted by capital R. Okay, so the extrusion ratio is nothing but the ratio of initial area to the final cross-sectional area. Okay. Where R is the extrusion ratio. A naught is the initial cross-sectional area. Initial cross-sectional area. And AF is the final cross-sectional area. Cross-sectional area. So basically, this term defines the amount of reduction which is obtained during the extrusion process. It relates the amount of reduction of the initial section of billet to the final section of the extrusion. Okay, and its value varies from material to material which is being extruded. So the typical values for steel are around 40:1, and it becomes around 400:1 for aluminum alloys or pure aluminum. Okay, so for steels, for steel, the R value is 40:1. And for aluminum, this becomes 400:1. Okay. But one should not get confused with the amount of fractional reduction or the reduction of area itself, or means amount of reduction that we generally calculate, which relates the change in area per unit area. That should not be mixed up with this. Both are different things, different parameters. We'll see the relation between those two. Okay, we can even represent this in terms of diameter if the cross section is circular. Okay, so let us assume that the cross section is circular in shape. Circular sections. So for circular sections, this R is nothing but initial area by final area. And we know that the area of a circular section is given as pi d square over 4. So pi d naught square, d naught for initial diameter over 4. And this will be divided by pi df square over 4. Okay. So ultimately this value becomes d naught square by df square, okay, in terms of the diameter. Okay, so this was the reduction ratio. Now, as I mentioned earlier, that the fractional reduction, or that the reduction that we measure in terms of fractional change in area is different from this. So let us see the relation between these two. Okay. So fractional reduction is basically given as so so fraction reduction. Okay. So this is denoted by R, and this is nothing but change in area. Definitely the area is going to reduce, so change in area will be initial area minus the final area. So change in area by initial area. This is the fraction reduction. Okay. And by the volume consistency, we can replace, or we can correlate the change in length also. Okay, so if we separate the terms, we will get 1 minus AF over you know. Okay, and by applying volume consistency, by volume consistency, we know that the area multiplied by length will be the volume. Okay, so this will be A naught, L naught will be nothing but AF LF. Okay, and if we rearrange these terms, we will get L naught over LF is nothing but AF over A naught. Okay, so now we know that the ratio of initial and final area can be written in terms of the extrusion ratio or the reduction ratio. Okay, so if we replace the terms here in this equation, say this is equation A. So if we put the value of extrusion ratio, we will get this from equation A, what we are getting is this AF over A naught will become 1 minus R, and if we take the reciprocal, then this will be A naught over AF will be 1 over 1 minus R. Okay, and we know that this A naught by AF is nothing but the extrusion ratio, capital R. So if we replace here, we will get the relation between the extrusion ratio and fractional reduction. Okay. So why we use reduction ratio is that the reason behind that is this parameter capital R clearly represents the large deformations. Suppose the area is reduced 40 times or 50 times, then it is clearly indicated by this reduction ratio, which will not be the case with the fractional change. Okay, so this is the relation. Now this ratio of initial and final length or ratios of areas can be written in terms or can be used to represent the true strain also. Okay. So the true strain is given as true strain. This will be nothing but ln of final length to the initial length, because we know that true strain is nothing but ln of 1 plus e, which is engineering strain, and engineering strain is change in length by original length. And if we substitute or replace the values, the change in length will be final length minus initial length divided by the original length, and that change, if we separate the terms, will become -1, and that 1 and 1 will get cancelled. So this becomes final length by initial length. Okay. Or this ratio, we have seen that it can also be written as A naught by AF from this relation. So this becomes ln of A naught over AF, and this A naught by AF is nothing but the reduction ratio. So this true strain becomes ln of reduction ratio. Okay. Also, this can be written in terms of the fractional reduction. So this true strain can also be written as ln of 1 over 1 minus R. So these are some relations which we will see in due course being applied to the extrusion process. Okay. Now, also the velocity of extruded product can be written in terms of this reduction ratio. Okay, so the velocity of extruded product is extruded product. Let us say this is BP. So this can be written as R multiplied by the ram velocity. This basically comes from the relation of the nature of equation of continuity, or that kind of similar relation. So this is also a very important relation in extrusion process. Okay. So here R is the reduction ratio. Reduction or extrusion ratio. Extrusion ratio. Okay. If we try to draw it schematically, how it appears is suppose this is the RAM and it is pressing this billet. So suppose if this is VR, suppose this is the extruded product. Okay. So its velocity will be Vp. So this Vp will be nothing but R into VR. So this Vp will be R times VR. So this is the relation. Now let us see the variation of extrusion pressure with the ramp travel, how it varies. And it will be an important parameter in case of extrusion. So the extrusion pressure is basically defined as the extrusion load applied divided by the cross-sectional area of the billet. Okay, so let us see how the extrusion pressure varies as a function of the ramp travel. Okay, so suppose so now we are talking about the extrusion pressure. Extrusion pressure. Move it a little down. Okay, so suppose my y-axis represents the extrusion pressure. Extrusion pressure. And the x-axis represents the ramp travel. So this will be ramp travel. So this pressure basically varies as so this basically varies in this way for the direct extrusion process. And for the indirect one, This varies in a fashion like it's almost remains constant, and then this goes like this. Okay. So this is the variation of extrusion pressure with the ramp travel. Let me call this as A, and this is B. Okay, so in case of the direct extrusion, the in case of the direct extrusion, the sudden initial increase is in the pressure is, this is not sudden increase, basically the continuous increase is basically due to the reason that uh, in the initial stages the billet flows or tries to fill the container completely on application of the load. So that's why this pressure keeps on increasing. Once the container gets filled, the pressure value reaches to the maximum value, which is known as breakthrough pressure. Okay, so this will be a point of breakthrough pressure. Break breakthrough pressure. Okay. Basically, the flow stresses are the stresses which will lead to deformation of this particular billet or material. Okay, so here this particular value of pressure is known as the breakthrough pressure, and once this value is reached, the container gets filled completely. Now the after this the billet will start to get extruded and extrusion process will begin. It will, the material will flow continuously under the flow stress, uniform flow stress. Okay, so let me write first that A is A here is for direct extrusion, and B is for indirect extrusion. Indirect extrusion. Okay, so the direct extrusion process, as I said or mentioned earlier, that initially the material tries to fill the container, and then the pressure keeps on decreasing because as the material flows out of the container, there is a reduction in the surface which is in contact with the container. So in turn, the frictional forces get reduced, and ultimately there is a decrease observed in the direct extrusion process. But if you see the graph of indirect extrusion, you will observe that the stress or the pressure almost remains constant and does not decrease as it is in the case of direct one. So what can be the reason behind this? Okay, so here we have discussed it earlier also that there is almost no friction between the billet and container wall in the indirect extrusion process. So that's why the flow stress will remain almost constant and material will flow continuously under that constant stress. Okay, so that's why this graph or this particular section of curve remains to be constant. Now, if you see towards the end, when the billet almost gets extruded out from the orifice, again the pressure starts increasing. This can be observed in case of both the direct as well as the indirect extrusion processes. So, why is it so? So, the reason behind this is that at last, the portion of material uh, which has all sort of defects or means foreign particles like some other phases or some defects, etc., that get segregated over there. They do not flow through the orifice and remain in the material, and that particular section is known as dead metal. So that particular section only remains there, and to push that particular portion out from the orifice, very high amount of stress or pressure is required. That's why the pressure again starts to increase after this stage. Okay, and that's why we do not consider that particular section, and that portion is generally discarded, that portion of billet. Okay. So if we try to see that also schematically, so how it appears is, uh, say at last, suppose this was the billet which was getting extruded. Okay. And it was flowing from the orifice. So at the end, some portion will be left out, which will be of no use. Okay. And it was being pressed by the ram. It say here the load was being applied. So this particular section now is full of defects, etc. So this portion is discarded. This is discarded. Because very high stress is required for its extrusion. Very high pressure is needed to extrude it. Okay. Extrude. So this gives us the variation of this extrusion pressure with ram travel. As the ram pushes the billet, these curves represent the variation of pressure in case of direct and indirect extrusion. Okay. So now let us see some other important things. So when in any type of machines, the load that we apply through the machine is not the actual load or pressure that get transferred to the sample. The load, basically the force is the actual thing that gets transferred. The pressure will be different. If we measure the pressure by cross section of the machine, or that means say tool or the component of machine which is in contact with the material, if we consider the cross section of that, that pressure will be different than the pressure which is experienced by the material. The pressure which is felt or experienced by material depends on the cross section of that material itself or the component itself. Okay, so in machines, this is an important point which will be valid for almost every case. Okay, in machines, if we apply pressure P by the machine, apply pressure P by the machine, then in that case, the pressure which will be experienced by the sample will depend on the cross section of the sample. Okay, so suppose we have a ram of cross sectional area A. Okay. So say some pressure gauge is attached to this. Okay, say some pressure gauge is attached here to measure the pressure, and this is the ram of area A. Then we first need to calculate the load which is being applied, load or force which is being applied due to this pressure measured by pressure gauge. This is pressure gauge. Okay. So here what will happen is the actual condition will be like this. Say this is my ramp, and here I have kept the sample. This is held on some holder or stage or anything like that. Okay, so this is the sample, and the ramp with cross sectional area A. This area is say A. This applies the load onto the material. Okay. So here this particular pressure, say P, it will not be applied on the sample. Here the force will be applied on this sample. Okay, and we can deduce the pressure acting on this sample through the cross section of sample itself. So this pressure P is nothing but force per unit area of the ram. This is the pressure applied by the machine. Okay, so let me write it here that P is the, let me change the ink color. So P is the pressure applied by machine. A is ram area. Okay. F is the force. Okay, so now to get the pressure on sample, we'll simply have to convert the machine pressure to force, and then we will use this force and the area of cross section of the sample to get the pressure. Okay. Now, so to get the pressure on sample, what we will have to do is to convert, we will have to convert the machine pressure to force. Okay, and then by dividing it by the cross section of sample or area of sample, we will get the pressure on the sample. So this force is nothing but the force that ram applies on the sample. Ram applies on the sample. Okay. Okay. And further, then we will You have to divide the force by the sample area to get the pressure on the sample. Okay, so let us say this is P prime or P dash. This is the pressure experienced by the sample, and this will be again this force, which we can calculate from the relation written above, divided by area of sample. You can use these two relations here. Again, this is sample area. Okay. So by this way, we can convert the pressure applied by machine to the pressure experienced by sample. Okay. Now let us see some special extrusion processes. Okay, so in this category, the first one is impact extrusion process, which is also known as Japan backward extrusion process. Okay, so we will now see the impact extrusion process. Impact extrusion process. Okay, and this is a type of cold working operation. Okay. Cold forming process, also known as Japan backward extrusion. Japan backward extrusion. So how is it done is there is a die which holds the billet, and there is a punch which comes from the top and presses the billet, which in turn gets extruded to form the final shape or product. Okay, so how it appears, let us see schematically. Suppose this is the die. So say this is the die, and in this die, the billet will be resting or will be put. So if this is my billet, and there will be a punch which will press it. So say this is the punch. Say this is the punch. Let us move it a little down. And this pressurizes the billet so that it can be extruded. Let me hatch it for better visibility. So this is our billet. This is the die. Okay. After this punch presses this billet into the die or mold, we get the final extruded product. Okay, so as a result of this, what happens is that say this is the die. This was the die. So the billet gets converted into the desired product. So it becomes something like this. It has been converted into the product. And the punch which pressed it is like this. This was the punch which pressed the billet to form this shape. Okay. So if we write down the names, this is the die. And this was the billet. Okay. And this is the punch. Punch. This is the extruded product. Extruded product, and this was our die. Here also, this was the billet. This was our die, and this was punch having the very high pressure value. Punch with high pressure. So using this process, collapsible tubes like the toothpaste tube, etc., are made. This appears like forging, but it is a type of extrusion process. When we will see forging, similar type of operation is done there, but this is not the same case. Here, billet is extruded out. Okay. So, as I mentioned, this process is used to make collapsible tubes. Used for making collapsible tubes. Tubes like toothpaste tubes, etc. Okay. So this was one of the special extrusion process. Another one is hydrostatic extrusion process. Okay, so in the hydrostatic process, as the name suggests, some liquid is used which in turn applies a hydrostatic pressure onto the billet so as to push it through the orifice in order to get the extrusion. Okay, so The next one is hydrostatic extrusion process. Okay, so let us see its schematic also. So this is very simple and easy to understand that how it goes. So this is our billet and it is being extruded to from the extrusion. So say this is the extruded portion and say this much portion is container wall. Here comes the liquid. So here there is some liquid. Let me write it in. Okay. There is some liquid. Which in turn will apply the hydrostatic pressure. And here the ram presses it. This is our ram. This was the billet. This type of arrangement is known as hydrostatic extrusion. So this is the ram. This is the liquid. This is the billet. This is extrusion. So this is how this appears. So let me write it also that in this process, a uniform pressure is applied by liquid. Uniform pressure is applied by some liquid on the billet. Okay. And the liquids which are generally used in this process are like castor oil, ethyl glycol, or mineral oils, etc. So liquids generally are say mineral oil, castor oil, or ethyl glycol. Okay. So since this pressure applies this process applies hydrostatic pressure, it can be utilized for ceramics also. Okay. So it will be relatively safer for them. this process can be used for ceramics. Okay, so actually, if we see the variation of pressure in this case, it will even fall below the indirect extrusion. Means it will be much more uh, constant type of curve. Let me draw it here again. So suppose we draw the graph again. We saw that for direct one, this was like this, and for indirect one, this graph. So this graph varied like this. It was almost constant. Okay. But for this hydrostatic extrusion process, it will be much more constant type of curve. So let us say this is something like this. So this is the extrusion pressure. Extrusion pressure. This is the RAM travel, and these graphs are respectively for direct extrusion. This one is for indirect extrusion. Indirect extrusion, and this below one is for hydrostatic extrusion. Hydrostatic extrusion. Okay. So in this way, this particular process is carried out. So now let us see another process which is used. Just we will see the overview how tubes are extruded. Okay, so tube extrusion process. It is done in a similar manner like these extrusions, but the only difference is that a mandrel is used as core, so to produce the hollow section of tubes. Tube extrusion process. This is not much different from these. So we will just see the schematic how this is carried out. So basically, say this is the part which is being extruded. Here it is the orifice, then a mandrel will be used here. So as to form the core. Mandrel will be used, and ultimately this will result in a product which would appear like this. So this will be like a hollow tube. Okay. This is just to indicate it will appear something like a tube which is hollow. This will be something like this. So hollow section like this will be formed. So this was tube extrusion process. Now let us see the die profile which is used for this extrusion process. Okay. So we'll now see the die profile. So let us see it with the help of schematics. So this will be something like this. This should be a little curve. Okay. Again, from here, this portion will be like this. It will go like this, and further similar will be at the lower side or bottom side. So this will be say these are the dies. Okay. So there are some terminologies associated with it. Let us see them. So the entry here is curved, as you can see here and here. The entries are curved so as to allow easy passes or easy entry of the billet into the die portion. So this is the curved entry. This is the entry. And it is curved. Okay. Again, here there will be the bite angle. So say this angle is alpha. This particular angle is alpha. The tapered section here is known as approach. Okay. So this section is known as approach. This is the approach. And after this, this angle again, it is the bite angle or also known as the approach angle. So alpha is the approach angle. Approach angle. Okay. The surface which is in contact with the billet is known as the bearing surface, and sometimes it is coated to reduce the friction because there will be a lot of friction when the billet passes through it. So this is the bearing surface. bearing surface, and it is sometimes coated. Coated. Again, the tapered section towards the end here is known as back relief, which allows the exit of billet easily. So this is the back relief. So this figure schematically represents the die profile of extrusion process. Okay. So now we are left with the relation of forces in extrusion operation or extrusion forming process. So we will see that in the next lecture, and then we will begin our next forming process. Okay. So we will end this class now. Meet you in the next class. Thank you so much.